Let's explore how the central limit theorem works. What I'm going to do is make up a population. Then I'm going to take a lot of samples from that population to see how the sample mean and sample standard deviation behave. According to the central limit theorem, the distribution of the sample mean should be approximately normal. Its mean should be the population mean, and its standard deviation should be the population standard deviation divided by the square root of the sample size. I'll set a seed so we can all get the same thing. I'm going to simulate a skewed population because I want a population that doesn't look anything like a normal distribution. I'll use the rchisk command. This will draw 100,000 numbers from a chi-square distribution. We'll get to the chi-square in a couple weeks, but for now, all you need to know is that it's right-skewed, and I want to make a right-skewed population. I'll save these 100,000 numbers as pop, and I'll draw a histogram, and there's my population. It's right-skewed, just like I wanted. The population mean is about 3. The population standard deviation is about 2.445, and I'm going to enter these as notes so I can keep track of them. These are the population values, remember. Mu equals 3, sigma equals 2.445. Now I'll take a sample of size 30 from this population. Sample pop 30, and I'll store this as samp. One thing to make note of is that I wouldn't want to name this thing sample because that's the name of a command in R. Sometimes it won't let you use certain words, but other times you can make a mess of things by having too many similar names. So it's a good practice to come up with original names for these objects you store. But anyway, I've got my sample of 30 from POP, which is this right-skewed population of 100,000. If I draw a histogram of this sample, I want it to look like a histogram of my population. And it does. It's got less detail, but it's the same general shape. I want the mean of my sample to be a good estimate of the population mean. 3.21 versus 3, that's not so bad. I want the standard deviation of my sample to be pretty close to the population standard deviation. And you see it's off by a bit, but it's not horrible. It seems like this sample is doing a decent job of describing the population, but maybe we just got lucky and got a good sample. If we randomly select 30 items from this population, how well can we expect the sample to describe the population in general? I'm going to highlight this code and run it a few times and see what we get. So that's not bad. That's pretty close. Again. Okay, so there's one that's pretty far off. The mean is 2.077 and the standard deviation is 1.64. The max is only about 6, but the max of pop is almost 26. If we got this sample, it could be misleading. What makes the central limit theorem so important is that it allows us to make probability statements about the sample mean. we can determine whether the sample mean we got was unlikely for a specified population mean. Now what I want to do is sample from the sampling distribution of the sample mean. As we've seen, the sample mean bounces around as we take samples. It's a random quantity that has its own distribution. The central limit theorem says that this distribution is approximately normal. So let's see. I'll take 1,000 samples and take the mean of each one. I make this vector called samp_mun for sample mean. I'm going to make a for loop, so this samp_mun is going to start off as 1,000 zeros. Rep 0 1000 will repeat 0 1000 times. And remember, I do this to make a placeholder for the data I collect in the loop. This is a simple loop. I take a sample from pop of size 30. I find the mean of that sample and I store it in the ith position of samp_mun. So at first, samp_mun is 1000 zeros, but for each iteration of the loop, that is, for each of the 1000 times that this loop runs, the zero gets replaced by a sample mean. And at the end, I have 1000 sample means. I took 1000 different samples of size 30 and collected their means. So now we can see how well the central limit theorem holds up. The central limit theorem says that they should follow a normal distribution with mean 3 and standard deviation 2.445 divided by the square root of 30. If I draw a histogram of samp_mun, it should look pretty close to normal. And it does. That's enough of a symmetrical bell shape for me. The mean of samp_mun should be pretty close to 3, and it is. And the standard deviation of samp_mun is 0.4355. The standard deviation of pop divided by the square root of 30 is pretty close to that. Of course, these numbers won't be exact. They're all random numbers, and the central limit theorem says that the normality of the sample mean is approximate and gets better as n gets bigger. Let's go back to that sample we got that was way off, where the sample mean was 2.077. How unlikely was that? How often will we get a sample mean that low from a sample of size 30 from this population? Since this sample mean follows a normal distribution, we can answer that question using p-norm. P-norm 2.077, and I want the mean to be the mean of pop, and I want the standard deviation to be the standard deviation of pop divided by the square root of the sample size, which is 30. That's the normal distribution that this sample mean follows. That gives me 0.019. There's about a 2% chance of drawing a sample mean 2.077 or lower from this population. How many elements of samp_mun were that low? Sum samp_mun less than equal 2.077. 8. 8 out of 1,000. 0.008.